Morty, we've got to turn the project in early.
Hey everyone, how are we doing? There is no project. Do not worry. Someone's like, project? What's going on with the project? No, there is no project for this class. I just like that opening. Worked really hard on that Rick and Morty effect at the end. One of my favorite parts of it, the electricity. I was like, I finally got to work after like a few hours one week, and I was like, yes, electricity effect on text. So cool. Awesome stuff. Who knows what topic we're talking about? Max, good to see you. Ballin, good to see you. Wilton, good to see you. Joshua, good to see you. Who all is in the chat? Anna, good to see you. Lillian, I think Anna was answering a bunch of questions on the Discord. Great job to everyone on the Discord. But who remembers what we're covering? Because Discord was really awesome. I look on the Discord and people are answering questions before I even get to them. Yeah, it was Anna. I gave a Mewtwo to that. Anna, thank you so much. You know what, Anna? We're throwing out some 500 points for Anna on the Discord catching a capitalization error. I saw that last night when I went to look at questions on the Discord. I go to the email, I go to the personal Discord messages, and then I hop over to usually the individuals. So I'm usually answering a bunch of stuff, and then I go eat some dinner, go take a break, hang out with my fiance a little bit. But definitely, Anna, those 500 points are for everyone answering those questions. So huge shout outs to Anna right there. Thank you so much. That's really what makes it. We don't want that sad music. We want this one. More chill music right here. Good to see you here, William. How's everyone doing today? Matthew, hey, what's up? How's everyone doing? People are just saying hi and hey. Sometimes I worry I'm not streaming. Sometimes I'm like, am I streaming? Am I here? Do I exist? Doing good. Yeah, shout out to Sienna right there. Sensational. Good. Go Vols. Did we win last night for the opener? I should look, right? Ballin's doing good. Emery's saying some go Vols right there. Well, today's topic is all about logistic regression. Happy right there. Awesome, Nathan. That's a good way to be. Good way to be happy right here. Let's go here and talk about some logistic regression. Got everyone woke up and ready to go. It's 1:12 in Knoxville. It's 12:12 here in Texas. Let's do this. Logistic regression. Here we go. So what's the deal with logistic regression? How is logistic different than linear regression? Who can explain, like, and this is usually where people get things wrong because they're going to use the linear equation, which is not what we use. This is like the biggest errors on the test. This is a no right here. That's a no. And this right here is a yes. What's the deal with this? Hey, Lindsay, great to see you here. So when we do logistic, why can we not use the irregular equation? Why can't we use that? Because what does logistic fit to it? Logistic is going to fit a what? So what does logistic fit? We'll see this here in a second. Like the idea of logistic regression is we're predicting probabilities for a categorical y, and we're not going to fit that line anymore, which is, we use the e raised to over the 1 plus e raised to. So we are fitting a what right here? Like what's the name of what we're fitting? Like when you hear logistic, you should think, oh, we're not fitting anymore. Two-level categorical and nonlinear, a sigmoidal curve. A sigmoidal. Oh, Whitson just crushing right there. Yep. And you are correct, Wilton. It is nonlinear. It does say nonlinear down there. And it's a sigmoidal curve. And sigmoidal means S shape. When you hear sigmoidal, think the S shape of the curve. So you can see here sigmoidal up and sigmoidal down. And this just goes to the sign of the coefficient. So the sign of the coefficient right here would dictate for you, does your logistic go up or does your logistic go down? I know that's the linear, but it's the same thing right here for the sign of the coefficient for an increase to the probability or a decrease to the probability right here. And you know what? Let's look at a model. We've got a lot of examples, but let's go look at a model real quick of this, and we'll come back here. But here we have a predicting whether or not a beetle will either live or die. I think there it is down there. We are predicting if it lives or dies. So what would be the level of interest? Would it be live or die? I think it's actually alive. So it's, it'd be live or die. Correct, yeah? You can see the answer down there. What would be the level of interest? Would it be live or die? So the beetle either lives or dies. So the beetle either lives or dies. What is the level of interest? Live, it is live, 100 points right there. It does say it on the slide too. And why is live the level of interest? So why is live the level of interest? When we were predicting whether or not a beetle lives or dies, why is live the level of interest? It is the last alphabetical. You got it. You know it. It is the last alphabetical. In logistic, the level of interest is last. Oh my gosh. But here's the big thing. When you do logistic, what two things need to change to do logistic regression? The two things that need to change when you do logistic versus regular old regression, the two things that need to change are you don't use the LM anymore, so put it in the chat as practice, because you're like, wait, my logistic won't run. I'm doing the final take home and it won't predict this variable. It won't work. Well, you might be doing logistic. You might be doing a categorical Y, so double check, am I doing a categorical or quantitative Y? And in this instance, the LM becomes a what? And we have to add an extra argument right here. I might still do y tilde x comma data equals. Yeah, I usually do the family after. So we have to do GLM instead of LM. So used to be LM. And this stands for a generalized linear model, which has different forms for it that we can use. It's a more general version of it, not just the linear model. GLM, well, and you got it right there. So we use the GLM instead of the LM. And then we also use family equals binomial to indicate that it's a two-level categorical. The default for this is Gaussian if you don't indicate it. So the GLM will actually do a regular old regression if not indicated otherwise. What do you think a dose of poison will do? Like how much was the dose of poison? What do you think poison will do to the probability of a beetle being alive or live? What do you think poison, which is the amount we dose them with, will do to a beetle being alive or live? You can, but some of the other follow-up codes, David, great question. You can, but some of the visualized things won't work. So it does work, like it will work, but don't do it because some of the like visualize and other codes won't work. Like check regression and everything will think you're trying to do a logistic. So the way Dr. Petrie wrote the code. So you can actually do it, but it'll cause a problem. So keep to the LM, but you could do different things. There's many different ways to do things. We just standardize it to everyone do the same. No, great. Such a good question. You can do it. And then you could just do GLM, y tilde x comma data equals, but then the visualization is going to think you're doing a logistic because it's going to see the GLM. And so check it out. Everyone's saying it's going to decrease it. You are correct. The probability of a beetle being live is going to decrease the more poison we give it. And look right here at this point. At this point, your predictions would what? Because this is the 50% barrier right here. Who can explain what goes on at this 50% barrier, which is sometimes something we have you calculate? What goes on? It's the 50-50 point, right? And how could you find this? The equation, which this is on the assignment, if anyone's been working the assignment, the equation is the negative intercept over the slope. So it's kind of a ratio of the two. So if you take the negative intercept over the slope, you can get to kind of where they balance each other out. And this is where we would change the predictions from yes to no. Does that make sense? Like after a dose of poison of 15.3, beetles are more likely to not be alive. Like they have the probability of not being alive is the higher one, or the probability of being alive is lower. So they would be more likely to be dead. I don't know what poison we're using or what, but apparently at 15.3, we think they're more likely to be dead than they are alive. So that is a very important 50-50 point. And we saw this last class. Let's check this out. So let's make a model right here predicting somebody, library, reg class, and of course you know where we're going. Come on. You don't got to ask. We're going to survey 10. I use survey 10 because it doesn't have variable names in it, but we're going to go M save into GLM. We're going to predict someone's gender from their weight, different model this time, data equals, survey 10, y tilde x comma data equals. And then we're going to do family equals binomial. I think it actually works if you put that parentheses still in there. It does. I think it used to not, because I would say it didn't, and then I tried it one time and it did. I like to make my code look like this, nice and neat. Can anyone tell me where the 50-50 breakpoint is? Who can calculate for 200 points where the 50-50 breakpoint is in this model? Who can calculate for 200 points? Take a moment right here, as though it's a test question. Where's the 50-50 breakpoint? I'm cheating. Where's the 50-50 breakpoint? I can tell if you're kind of right. At what point would we predict? Oh my gosh, Joshua just destroying it. Joshua, that's worth the next 300 right there. See if you can find what Joshua did right here. He took the negative intercept over the negative Yep, that's right. The negative intercept over the slope. People might be carrying decimals a little bit differently. And think about what I did. How did Brian kind of do this in his head? What did Brian use to do it in his head to be like, And then I'm like, yeah, that looks right. How is Brian doing it in his head here? Negative intercept over slope. And there's the answer. How was I like double checking your work right there? How was I double checking? I think Kevin might have done what I did. You can roughly see it on the graph because here's the 50 point in tracing down. It's somewhere around here. And you could confirm this on your graphic by going here and going to your visualized model, going AB line. We're appending code to it. Go vertical equals this with a col equal red and line width equal to 3. There you go. That's where it is right there. That's where it intersects. And you can see this is the point. So good stuff. We can zoom in really big on it. Yep. That's where it hits right there. 50-50 breakpoint. So pretty good stuff. Know how to calculate this nice and easy. If you get a test question like that, oh, negative intercept over the slope. And once again, you do get your cheat sheet. So cheat sheet, a big help right there. Is that AB line something from reg class? It's a base R function, I believe. When we say base R, those are the things that are in R all the time. It probably says base next to it. Oh, it's in graphics. So it's in the graphics library. So it's AB line. I call it AB line sometimes, but it's AB line. I know cheat sheets are so awesome. And that just lets you append on lines to graphics. So like you can add an extra line. You can add points. You can add text to graphics. There's so many cool things you can do with graphics. So R is really good about that, especially if you get into ggplot2, which we do in our later classes. There's one more thing I was going to mention. What do you think weight does for the probability of somebody being male? Like just think about this. 2 individuals who differ in their weight by 1 pound, the person who weighs more would what? And I just interpreted the coefficient. 2 individuals who differ in their weight by 1 pound, the individual who weighs more is what? Now be careful, this is not going to be interpreted as a coefficient anymore. 2 individuals who differ in their weight by 1 pound, the individual who weighs more is what? Just think about what this tells you and what you know about the world. More likely to be male. We just interpreted the coefficient. 2 individuals who differ in their weight by 1 pound, the individual who weighs more is more likely to be male. That's it. That's the full interpretation. Is more like, be careful, not expected, because what if they're down here and someone weighs 100 and someone weighs 101? So would you expect the person who, yes or no, would you expect the person who weighs 101 pounds to be male? It's not that they can't be male. My friend John, he weighed about 100 pounds in high school. So maybe, I don't know if this high school students or not, but then let's say John has a friend who weighs 100 pounds. So John weighs 101. And so John would not be predicted to be male, but John would what? So go with what Joshua said right there. John, compared to his friend who weighs 100 pounds, John would be what to his friend right here? Not that John will expected to be male. John is what to be male than John's friend who weighs 100 pounds. So we have 2 individuals who differ by 1 pound, where one weighs 100 and one weighs 101. John is more likely to be male. Now, John is male. John would be predicted to not be male by this model. Can we determine how much more likely someone is to be male, 1 pound weight different from this output? It'd be harder to by this output, because what do you notice? And that brings us back to the notes right here. What do you notice about the logistic model versus the linear model? What do you notice about the differences between 1 unit differences? This is the key thing to notice. In the linear model, the differences are constant, but in the logistic model, the differences on 1 unit differences. So the differences here on 1 unit differences are what? Because in the linear model, they're constant. It's like 2 individuals who differ by 1 unit of x are expected to differ by blank units of y, where the individual with the higher x is expected to have a higher y by this much. And they are dependent on the x, correct? And they're not what, though? Because here, this is a big difference, and here, this is a little difference, right? So you can see right here, the differences are not, oh, you said, yeah, you got the notes right up right there, right? They're not the same exactly. Since it's non-linear, a 1 unit difference is not always constant. And so you might be wondering, why don't we interpret the coefficient? Well, the coefficient's not a linear coefficient. Put this in the chat. I will give up to 500 points for every 2 people who say this. So I'm going to count up how many people say it. It's 50 points per person. So we can get up to 500 points. Do not mention the value of the coefficient in logistic. Do not mention the value of the coefficient in logistic. Please put that in the chat. That's one of the biggest errors I see. Do not mention the value of the coefficient in logistic. 50 points for every person who writes that. This is something you must write down. Do not mention the value of the coefficient in logistic. I'll count how many people say it a moment here. We do not mention the value of the coefficient in logistic. I'm going to go out on a limb and say we got those 10 people saying it, but we do not mention the value. What is the only thing that matters when it comes to the coefficient in logistic? What do you think is the only thing that's going to matter about this X coefficient in logistic? Just a 4-letter word. I saw the what. Let's look at the what of that coefficient. What's the only thing that's going to matter about that coefficient? The sign. Another 100 points in the chat. The only thing that matters is in the sign, because if it's positive, it's going to be sigmoidal up. Where if it's negative, we need to remove this from the graphic. If it's negative, it's going to be sigmoidal down. So if you look at this one, two individuals who differ by their GPA in 1 point, the individual with the higher GPA is what? So two individuals who differ in their GPA by 1 point, the individual with the higher GPA is what? Two individuals. I like that right there. I almost want that to be a quote. Two individuals who differ in their GPA by 1 point, the individual with the higher GPA is what? Two individuals who differ in their GPA by 1 point, the individual with the higher GPA, kind of. This model is set up male-female because it is binomial. I would say less likely to be male. True for this, the way this data is composed. I would probably say, because think of this is going to lower the probability of the level of interest. So I might keep it to saying less likely to be the level of interest, which means they're less likely to be male. Does that make sense? And this data is set up male-female. So it is true what you're saying, that they would be more likely to be female according to this predictive model. And I would probably say less likely, like there is a lower probability for individuals with higher GPAs, like two individuals who differ in their GPA by 1 point. The individuals with the higher GPA is less likely to be male. That's just the way the world works. And so you can see after you get to a GPA of about 2.8, see, I'm down here in this reason, high school GPA. When you get to about a 2.8 GPA, and we could find out where that GPA is, negative intercept over this right here, and it's negative over that. So it's 2.8. And think about how quick I was able to guesstimate that from the graphic. Once again, I said about 2.8, and that's about what it is. It's about 2.8. And that's the point at which we would predict somebody is female. It doesn't mean they are. It just means that this is where the prediction changes. Once again, this data is set up to be male up here, female down here. And yeah, that's how we interpret it. And we do not mention the coefficient because the coefficient is not positive. There was one last thing mentioned. I think it was, did Wilton mention it or Whitson? Someone said something about what are the differences. So to find the differences between these people, I'm actually going to go back to the weight version because that one's a little sharper. There's a little stronger. If you look at the p-value especially, you see the p-value there versus the p-value here. Does it make sense that this is a stronger relationship? Why is this a stronger relationship? Explain to me why this curve right here has a stronger relationship, there it is right there, than this curve right here. Explain to me why the relationship, here's this curve right here, and then here's this curve right here. Explain to me why this has a stronger relationship. And you see it right here in the p-value. So this is the p-value of this curve, and remember it has a positive coefficient, which means it's sigmoidal up, and this one has a negative coefficient, which means it's sigmoidal down, and there's the curve associated with it. So why is it stronger? What does stronger mean in logistic? If you see a stronger logistic form, yeah, and there's a stronger relationship. And so, Joshua, you're right there, 100 points. Weight is a better explanatory variable. So you see a sharper curve. Strength of logistic is going to be how quick it kind of changes in nature of sharpness of the S-curve. So the strength of a logistic curve is going to be how sharp the S-curve is. Think of it as like a hill. And the strongest logistic curves are going to be like really sharp. And so the stronger, it follows the sigmoidal shape better. Yep. You know what's interesting? The worst sigmoidal shape is actually a flat line because then the probability doesn't change and it would be like the naive model. More on that to come. But I think the question was, how could we find out the differences in probabilities? And to do this, we actually have to get new data. So the new data right here, let's store into it a data.frame. And let's take the X variable of weight and assign values of weight for somebody who is 100, someone who's 101, and somebody who's 150, and someone who's 151. So we go here to predict using our model, and there's the predictions. Let's go to new data equals new data. Now I always get this next argument wrong. It's going to be type equals, but I do not remember what the type is supposed to equal. It'll help me out though. It'll tell me you got it wrong. I'm going to put prob, and it's going to say, nope, type needs to equal, and it should be, I think, response. And there we go. So when you look at these right here, this person has a how much more, and I just want you to round it. How much of a difference is there between the person who was 101 pounds and the person who was 101 pounds? How much of a difference are there in their probabilities? So the difference in probabilities between this person and this person on their predictions of them, the first person here being male and the second person here being male, is a difference of only about what? It's smaller than that. It's smaller than that for these two people. This one is only a difference of about 0.2. Does that make sense? You can mathematically find it if you want. These two individuals have a difference in their probabilities. It looks to be about 0.2-ish. And there it is right there. Does that make... exactly. Don't worry. 100 points. Good work right there, Josh. But these people towards the sharper part of the curve, what is their difference? So the difference... Oh, Joshua, I see what you did. You did the next ones. These are the people who weigh 150. That's the prediction for the person who weighs 150. And this is the prediction for the person who weighs 151. Do you see the order to it, the way I did the predictions? So those are the predictions in the order they go for each individual. And Joshua is correct. Joshua, great work following along right there. The difference between these individuals is a difference of this. And what do you notice about these differences in probabilities for 1 unit differences? Please repeat this because we don't mention the coefficient, because the differences here between these individuals who have a 1 unit difference is not this. It's not this. The difference is it's not constant. Totally exactly what I wanted to hear. It's not a constant difference because the curve has it's sigmoidal shape. So if you're towards the less slope part of the curve, you're going to see smaller differences. But when you get to the sharp part of the curve, you're going to see bigger differences between people with 1 unit differences. So these people are a 1 unit difference with a larger difference. These people right here are a 1 unit difference with a smaller difference because they're towards the lower part of the curve. That's all we're doing right here. Let's hop back to the main screen. Okay. So all we're doing right here is trying to solve out the logistic curve. And I think that's got everything right here. Don't worry about maximum likelihood principle. I guess if you want to take one note, the coefficients right here are found by the maximum likelihood principle. I can't promise I won't put this as a multiple choice question on the test. It's the only thing, if we put a test question that has you doing this, I'll just scream, and then I'll remove it. But the coefficients are found via the maximum likelihood. If you're creating your cheat sheet, the coefficients are found via the maximum likelihood principle, which maximizes the chance of reproducing our data. That's to say, when we create this sigmoidal curve right here, so we make a curve that goes through our data, it's going to try to properly classify the groups right here. And the coefficients we take are going to be the coefficients that optimize how correctly we classify the data points. So if you just literally want to take that sentence, that's about as far as we could go on this. It's just that the coefficients for the curve are the coefficients that maximize the amount we classify correctly, and that's how we find it. It'll all be done in the background for you, nice and easy. And yeah, let's continue on. When would we predict somebody is going to be male? So we were just looking at some curves right there. When would we predict somebody is male? When would we predict somebody is male? When would we predict somebody is male? Do you remember right there with the models you were just looking at? When would we predict someone is male? Who knows? Correct. And that's because the coefficient was positive. Because we had a positive slope right here, the people who had higher weights were more likely to be male. So when the slope is positive, the probabilities are higher for people with larger X's. But if the slope is negative right here, great job right there. When the slope is negative, well, then that's going to decrease probabilities right here like this. More than 50% exactly. So if you reach past that 50% point, we will make this prediction, and we can calculate that 50% point by doing the negative intercept over the slope. I'd also put this on the test right on your cheat sheet. Thank you for cheat sheets right there. Exactly. And we'll do some more interpretation right here for talking about coefficients a little bit. And let's do this. Here's solving the equation. We did this last class, but please be able to solve this by hand. Let's do a practice. We can't do more than enough practice because I know what people miss on the test. I'd like for you to take your weight right now, as long as you feel comfortable. Take your weight and solve for your probability of being male. So can you use the equation right here, as long as you're comfortable doing that, and solve for your probability of being male? That's what the model predicts. So what is your probability of being male? See if you can do it. I'll be able to tell if people did it properly, as long as you feel comfortable, and put it in the chat. So no points, 100 points for everyone, just anyone does it. But you don't have to do this. Who can do it? Take a moment, try to solve the equation, and then I'll solve it. I'll start the work here in the background so you can see it. So I don't want you to see the answer quite yet, because there's going to be steps people forget, and this is where people make an error. Let's go start answer. Well, let's call it X. I'm going to call it X for the moment. And we're going to go here. And that. Nope. Call it W. What do I weigh these days? 170. Anyone have an answer? My probability of being male. Don't worry, I'm purposely making an error here. Is that my probability of being male? Ooh, that's interesting. Let's raise up this to 200. Is that my probability of being male? Something's going on right here. Something's going on. It didn't change. Oh, did I not rerun it? Haha. There we go. Now I probably is 2.3% or 233%. Ooh, does anyone know? There's a huge error right here that a lot of people make. And it's on the slide that we didn't do it properly. I actually solved for this. If you look at my work, I solved for that. I solved out the equation. Does anyone know? So we have to do e raised to what we found over. Yours is 0.366. Now, so let me ask this though, because you might have, you maybe, I don't know, but let me double check. So if you did this right here, this is not the answer. What you have to do once you solve this is you have to take e raised to it over 1 plus e raised to this. And there's the answer. And 92.5, there you go. I think David, did you do the e raised to the over the 1 raised to the over the 1 plus e raised to the? And what you should do is you should look at this curve and say, if I weigh about 170, then if I trace up and over, 66 sounds like the right answer. And funny enough, we basically got that right here. Yep. So if you weigh 200, then you would go right here and trace up and trace over. If you weigh like 100, you'd go up here and trace over. So where the error usually occurs is people put a weight of 100 in, they solve out, they get X. And if you get X right here, you'd say, wait, I have a negative probability? Ah, yes. Did you do it? Well, you did? Okay, yep. So what do you notice here, since this gives a negative number right here? This person with a negative number would be predicted to be what? Since they have a negative for the number for the X, this person right here, which is a quick solve, you know they're going to be predicted to be what? Since this is negative, anything that's negative would be predicted to be what? If it's negative, the person would be predicted to be what? Female. Does that make sense? But if it's positive, like someone who's like 180, well, then they would be predicted to be male. That number there is positive when we solve the equation. So really it becomes, what is the value of the equation? So when you solve the equation, you then plug whatever that equation is into the e raised to over the 1 plus e raised to the. This is where people don't do this on the test. Like we say, predict the probability of this, and then they say 2.8. And it's like, no! But if you were to find, when you run this equation, and you got 2.8 for this, now I don't want you to solve this, but just tell me, you know that this probability has to now be more than what? When you if you solve the equation, like if you were to do the regular old regression, but you have to do the probability now, the probability you get should be more than this. it should be the level of interest, hint. So the probability you get by solving the e raised to the over the 1 plus e raised to the, it must be of this probability because it's going to be the level of interest. So what would it be? It must be greater than this value. I can say with 100% certainty that it will be greater than this. And I'll show you. Since the number here is positive, just theoretically, if it were to solve the 2.8, I know the probability must be more than 50%. Because anything that has a positive value would be the level of interest, and anything with a negative value would be not the level of interest. And if we solved out for one that was 0, it would be exactly at the 50-50 breakpoint. Like if we theoretically put in something close to 157, that would solve out to about 0. And that'd be close to the 50-50 breakpoint. I think it was like this. And so that's close to the 50-50 breakpoint. Does that make sense, Joshua, right there? That if the equation solves to a positive number, it will solve for the level of interest, which is something above 50%. If the equation solves to a negative number, it'll solve to something that is not the level of interest. So just looking at the equation itself, right here at the 50-50 breakpoint is where it'll be 0. Anything that solves out positive is over here, and anything that solves out negative is over here. The 50-50 breakpoint is where this equation solves out to 0, but you must run it through the e raised to the. So anything with a positive solve has above a 50% probability. Anything with a negative solve has below a 50% probability. Anything exactly at 0, which I missed the mark because it's a little bit over here. Anything exactly at 0 would have a the 50-50 probability. So good concept stuff right here. Yes, so positive solves for level of interest of male, but when negative solves for the non-level, exactly. So anything like you could, like if I said, like great answer right there. Imagine we had someone like, pretend you can't see the graphic, boop, because that gives the answer away. If we had somebody right here who weighs 145 pounds, so just knowing this number right here, are they going to be the level of interest or not the level of interest? Just speak to me that way. Yep, that's exactly what that is, Nathan, right there. That's the e raised to the over the 1 plus e raised to the. Great answer. So since this is the value of the equation, when we put it into the e raised to the over the 1 plus e raised to the, are they going to be the level of interest or not the level of interest with this? So that's before we solve it through the equation. Is it going to solve out for someone who is the level of interest or who's not the level of interest? When you see this right here as the solve for the equation, not the level of interest. Veda, great work right there. And since that's not the level of interest, that means the probability has to be what to 50%? Like when I solve this right here, now the probability has to be what to 50%? Because they're going to be not the level of interest. So if they're not the level of interest, the probability I get from solving this must be what to 50%? Because they're not, less than. There you go. So this is the theory we should understand about how this works. And once again, if we visualize this, we could see a good guesstimate of it. We said that they weigh 145, so they're over here. Yep, so about 32%. Looks pretty good. Awesome stuff. That's how we use this equation. You can see another solve here on the screen, just going through doing the e raised to the over the 1 plus. I prefer to solve this by itself and just call it x or something and manipulate the variable by changing what the x is. I think it's a little bit easier. Great work. And once again, this is where I usually see people just like not knowing what they're doing. They're like, wait a minute, how could I solve out? Like imagine I give a beetle, and you could do this solve pretty quick. I give a beetle 5 units of poison. Do you think that beetle will be alive or dead? Someone right here in the chat, tell me. I give beetles 5 units of dose of poison. Would you predict that beetle would be alive or dead with 5 units dose of poison? So just think about multiply this by 5 and add it to the intercept. What would the number be still? The level of interest is alive, and right there, Nathan just destroying it. Yep. And so we can solve it out. We can solve the whole thing out, but you're like, the equation still is positive. Does that make sense? Using the knowledge we have right here, the equation would still be positive if you go multiply this by 5 right here. You plug in 5 and multiply, so it'd still be a positive number. Exactly. David, you're seeing it. That's the algebra. You're literally solving. You would said 0 equals this, and you're solving for what would equal. Exactly. That's exactly what you're doing when you're solving that equation. It's the equation to solve for at what value it'd be equal to that. That's exactly what you're doing. It's algebra. Maybe it helps to better understand it that way, but yeah. David, yeah, exactly. That's all you're doing. You're just solving an algebra question for when does this equation equal to 0? 200 points, David. See, it all goes back to just kind of mathematics. And here's solving for a dose of 20. So all you're doing is plugging in 20. And when you plug in 20, if you look at 20 right here, timesing this by 20 is going to make enough so that the equation is negative. I just like to look at this right here and be like, okay, the equation is negative, so the probability is going to be not the level of interest. And it's pretty clear to see, will those beetles be alive at 20? No. They're not going to be alive right here. That is a big no. That falls right on that no right there. Beetles are not going to be alive if you give them 20 units of poison. It's a lot of poison. Donations to charity. We have, will people donate or not donate? So what is the level of interest right here? Will they donate or not donate? Real quick, 2-letter word in the chat. Will they donate or not donate, or no? That's the level, is no. But will they donate or no donate? Which one is the level of interest? Which is kind of weird. You could reset this. You could change it. You could re-level stuff and do all that good stuff. And I want you to think about this. What we have right here, not donate, exactly. Not donate is the level of interest because it's the last alphabetical, because the variable is donate or no. And so the last is no. So when somebody's log income, which is basically income, when someone's log income increases, the probability of them not donating what's is. When somebody's log income increases, the probability of them not donating what's is. And I think it's not going to look as sharp as that. When somebody's log income increases, the probability of them not donating what's is, because it's going to be a double negative, you hear it, decreases. So great job right there, Veda and Nathan. When somebody's log income, basically two people who differ in their income, the person with more income is less likely to not donate. But I'd probably change that for my boss, and my boss would probably say, of course, two people who differ in their income, the people with more money are more likely to donate, because less likely to not donate is a double negative. We could just change that to more likely to donate. And what do you notice about this model? What do you notice about this model? What's it going to predict for everybody? What would this model predict for every single person? I'll give you a hint. What does this model predict for every single person? Every single person would be predicted to what? Predicts no one will donate. It's going to predict no one donates. Every single person in the data set, unless we go further out, would be predicted not to donate. What do you know about this model? This model is predicting will people donate again? And you might say, Brian, that's a line. No, it's not. I said, no, I know it's a line. I saw you make those errors during office hours. That's a line. No, it's not. It's when you zoom in on an S-shaped curve, like if you go to an S-shaped curve and you zoom in on a portion of it, it may look like a line. But in truth, we're just seeing only a portion of this S-shaped curve. We extend it out further. But also this curve here too does not actually dip below the 50%, I think. And you'll notice it because both coefficients are positive. So you'd have to actually go to a negative months since last gift. But what do you notice about last gift right here? Last gift is very, 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 very ridiculously statistically significant. And the people who have taken longer to donate would be more likely to not donate. Like, just think about this. You have people who've been donating to you for years, and then it's been a long time since this person donated. They're probably going to be less likely to donate now than someone who just donated in a recent campaign. So you're like, we need to get donations. Who do you go to? The people who just donated. I know that sounds crazy. Like, you just donated. Well, they're more likely to donate than people who have had a longer time since their last gift. We were trying to reach out every 6 months or so. But yeah, months since last gift, the more recent they've donated, the more likely they are to donate again. And just, I've had to deal with some donor stuff, and it pretty much works that way. If people donate, they're more likely to donate again. I donate to UT. Yes, do it. Get to donate to what you want to. So I'm like, yes, I'm going to put my money here. So here is the S-shaped curve we see right here, telling us right here that we cannot predict that people would donate. And that's basically the logistic regression. But here's the thing. How hard do you think multiple logistic regression is going to be? Because when we say multiple logistic regression, what's about to change in your world? What is the only thing that's going to change if we do multiple logistic regression, which just, I promise you, is not that hard. You'll look at this and be like, really? That's all it is? I hope. I hope you look at it and say, wait, everything you just taught us there applies to this. In multiple logistic regression, what do we have? What's going to change about multiple? When we say multiple regression, multiple logistic. So logistic means it's a categorical X. Important we know that. More predictors. That's all it is. When you say simple logistic, that just means 1x. When you say multiple logistic, multiple x's, that's all it is right here. And take a look. Same equation. All you have here is multiple x's. And then what do? E raised to the over 1 plus e raised to the. Once again, all you would do is solve the equation of e raised to your regression equation over 1 plus e raised to your regression equation. On a scale of 1 to 10, how hard does it look to go from logistic to multiple logistic? So all you're doing is just using the same regression equations we've been using with the intercept plus the first coefficient times the first x plus the second coefficient times the second x plus the blank times the blank times the blank times the blank. And then you just do the e raised to that over the 1 plus e raised to that. It's the same equation up here up top as it is right here. And it's e raised to that, and I usually just call it x. Like e raised to that over 1 plus e raised to that. And that's what gets you the logistic shape. So the very important thing, which so many people forget when they get to the test, is you have to run it through this, because this will get you the probabilities and fits the logistic form to it, rather than up here, which we do not want to apply. This is the linear form to it. So do not use the top equation to solve for the final answer. The equation must then be ran through the e raised to the over the 1 plus e raised to the to find the logistic form for it. So when we have quantitative variables, two individuals who are otherwise identical, why are we saying otherwise identical? When do we say otherwise identical? Two individuals who are otherwise identical. Why are we saying otherwise identical? Two individuals who are otherwise identical, the one with the larger value of x is more likely to be the level of interest. If we have a negative coefficient, two individuals who are otherwise identical, because it's a multiple. Yep, anytime you're in a multiple, you have to say, but they're otherwise identical. You can say with holding everything else constant. There's okay ways to say it, but I usually just say otherwise identical. Like these two things that are otherwise identical, but they differ in this x by one thing here. Exactly, we have two or more predictors. Great job right there. But what about if it's an indicator variable? So now we must compare the indicator variable to the what? So if it's categorical x's, we must compare our indicator variable to a what? If it's categorical x's, we must compare our indicator variable to a what? So whenever you have indicators, you have categorical x's like two individuals where one is in a fraternity, sorority where the other is not. I'd have to compare it to what? And it should be, which one of those would be the reference? Would be first? Yes, no. So the reference would be, it'd be no would be the reference. The reference, exactly. I was mumbling it there in the background. So two individuals who are otherwise identical, where one is represented by the indicator and the other is the reference. If there is a positive coefficient, the indicator would indicate that they're more likely to be what we're predicting. If there's a negative coefficient, they'd be less likely. We'll look at some output here in a second. So here we are predicting whether or not someone has diabetes. So with this, we are going to predict yes or no. Which one of these is going to be the level of interest? We have yes, which is last alphabetical, and we have no, which is first. So which of these will be the level of interest? Which one of these will be the level of interest? We have yes, someone has diabetes, and we have no, someone does not. Yes, because it's last alphabetical. I was trying to block it right there. We are predicting yes because it's last alphabetical. So let's take a look at the data. So here we are. We have all these different variables. We don't have a categorical one in here yet. But what looks to be the biggest indicator, like just looking at this data, what brings with it the most new information? Just look at the variables, look through the data, and tell me which of these, and it should be kind of obvious with what you think right here, when it goes to predicting whether or not someone has diabetes, which one of these brings with it the most new information not accounted for by the other variables? Probably is doing that. Like it brings with it something really special that is like, hey, you know, you're here with all these variables, but you're super important. Which one of these is super important right now? Glucose, Veda, you see it, yeah. And pretty obvious when you think about predicting diabetes. Glucose is doing a bunch of things that the other ones are not, because we have right here, you know, like super statistically significant. The other ones might be important by themselves, but body fat, blood pressure, maybe due to variance inflation, are overlapping in what they bring. But glucose is super important. So two women who are otherwise identical, they've had the same amount of pregnancies, same body fat, same insulin, same BMI, same age, same blood pressure. But one of them has higher glucose. The one with higher glucose would be what? The one with higher glucose would be what? Two women who are otherwise identical, but they differ in their glucose, where one has higher glucose, we could say by 1 unit, but it just doesn't matter about the units anymore.
It doesn't matter!
Because we're not going to interpret that coefficient. Two women who are otherwise identical, but one of them has higher glucose. The woman with higher glucose would be what? And what you want to look at here is this a positive or negative coefficient? So two women, more likely, exactly, that's just it. Two women who are otherwise identical. And if you're talking to BAS, you would just say, yeah, we noticed in the data that higher glucose is generally associated with being more likely to have diabetes. You might say who are otherwise identical, but we know mathematically that's what it means. On your test, make sure to write two women who are otherwise identical but differ in their glucose by 1 unit. The woman who has higher glucose is more likely to have diabetes. We sometimes try to make it, be very exact, and then we can shrink it down to something easier sometimes. And just coefficients right here. How about we have people who are going to leave their cell phone carrier? Once again, we are predicting if someone will leave, but now we have some categorical variables. How many categorical variables were in this model? I'm even double checking my check right here. How many categorical variables were in this model? Who can see where the categorical variables are? And who knows, for 100 points right here, who knows how many categorical variables are in the model? How many categorical variables were there in the model? Look through the data right here. And we're predicting if someone will leave their cell phone carrier. So we are predicting yes, someone will leave. Will someone leave? Churn is whether or not you leave your cell phone carrier. We're predicting if someone will leave. So how many categorical variables were there? Whitson, you crushed it, man. Great job. There's 2. This right here, because what we notice is why don't we see international plan? No. Why don't we see international plan? No. That's just a quantitative variable right there. These are all quantitatives. Why don't we see international plan? No. I'm highlighting the quantitatives. The categoricals have their indicator level. Why don't we see international plan? No. And voicemail? No. Why? We should see those, right? Why don't they exist in this data? Surely there's people without an international plan. Surely there's people without a voicemail plan. Back in the day when you have voicemail plans. Surely. Reference level. Great job. Another 100 points. They're the reference level, so you don't see them. The reason I've highlighted it this way is I want to illustrate to you that we have 2 types of X variables in this model. We have quantitatives, so 2 individuals who are otherwise identical but differ in their account length by 1 year, let's say, because I don't know, it doesn't matter on the units.
It doesn't matter.
2 individuals who differ in their account length with us. The individual who has who are otherwise identical. The individual who has a longer account, is more likely to churn. Doesn't bring with it new information. But is more likely to churn. 2 individuals who are otherwise identical, but differ in their number of calls to customer service. And oh my gosh, look at that. 2 individuals who are otherwise identical, but differ in their numbers of calls to customer service. The person who has more calls to customer service is what? And churn means leave your cell phone carrier. That's what churn is. 2 people who are otherwise identical, but differ in their calls to customer service by 1 call to customer service. The person with more calls to customer service would be what? And we want to look here and see, very important, this is a positive coefficient. It's the only thing we care about there. 2 individuals who are otherwise identical but differ in their calls to customer service by 1. The person with more calls to customer service is what? More likely to churn, more likely to leave. Matthew, great job right there. More likely to leave, churn. That's what churn means. So you can call it leave if you want, like leave their cell phone carrier. What do you notice about having an international plan? Ooh, I'm going to put 500 points out here. Big 500-point bonus question of the day. Interpret the coefficient of international plan. If you can do this, you understand how to do this. Take a moment. We try to do this because these are on the final. No joke. Have this on your cheat sheet and know how to do this. Remember, we're predicting probabilities. We don't mention the coefficient. Take a moment right here and see if you can do it. First person gets the class 500 crazy points. So how would we interpret that coefficient? I'll highlight just the coefficient. Remember, we're predicting whether or not someone leaves, so it's the probability of them leaving. How would we interpret this coefficient right here? That's a categorical indicator. Close, Nathan, and expand upon it. That's part of it, Nathan. You're on the right track. I mean, basically. Yeah. Nathan, put the whole thing together. Oh, wait, you forgot a major portion, though. Yeah, I know. We'll put this all together. We're getting the components right here. It's like you gave me a sandwich, and you're like, you put it on like different plates. You're like, here's your bun, here's your meat, here's your cheese. And I'm like, can you just put it to the cheeseburger? Put it to the cheeseburger for those 500 points. We got the bun, the meat, the cheese. Put everything together. I just want a cheeseburger. 2 individuals. Now you just stacked. Now you put your cheese on top of the bun. You said, okay, here you go. I'm going to take your burger, put it in the bun. I'm going to put your cheese on top. I say, I like it in a certain order. Just so close. These are our big 500 points. Good practice right here. Who's got it? This is really good practice. You'll be writing this out later. We're so close. Who can write out the full thing in the right order? We're so close. I was looking at the voicemail playing coefficient. Oh, yeah. What is the right order of these? We're so close. We're so close. So close. So close. So close. 2 individuals who are what? We're so close. A little more chill music right here. Brian, close, Brian. But Murray, it's going to be we have to compare the indicator to the reference. We have to compare the indicator to the reference. Between two otherwise identical individuals, where one has an international plan and one does not, the one with a plan is more likely to churn. Great job right there. That's got it. 2 individuals who are otherwise identical, or one has an international plan. Pretty much. I would accept that, Nathan. I like the way Wilton did it right there, but with Nathan, I'd probably accept that. Max, 2 individuals who are otherwise two otherwise identical individuals. There we go, which is fine. 2 otherwise identical individuals who differ in whether or not they have an international plan. The one with a plan is more likely to churn. Great job. Good practice right here. So why is this one a little bit different than the other ones we've been doing? Why is this one a little bit different right here? Why are these 2 a little bit different? Why are those 2 a little bit different than all these other ones around here? Where we have to compare it, where we have to say like 2 individuals who are otherwise identical, or one has an international plan and the other does not have an international plan. The one with an international plan is more likely to churn. Why are these a little bit different interpretation? Which is the big point to illustrate on interpreting these. Like 2 individuals who are otherwise identical, but one has more total evening charges. The one with more total evening charges is more likely to churn. I didn't mention, I didn't compare it to anything down here. I just said, exactly, the categorical you have to compare to the reference. So if it's categorical, you have to compare to a reference. 2 individuals who are otherwise identical but differ in their calls to customer service by 1, the one with more calls to customer service is more likely to churn. Knowing how to compare these is pretty important. And you can see right here, interpretations for you. So going through interpreting, very important. The curve changing. Yes. So what do you notice right here? When we do this right here, the curve gives different probabilities depending right here. We have 2 variables right here showing implicit lines. We don't solve a lot of implicit lines, but now we have our implicit lines for the sigmoidal curve. And notice how the curve gives different probabilities when we solve in and get the implicit curves for the sigmoidal. Just solving through, plugging in the values like we've been doing, and we will do some examples of that. But statistical significance, pretty easy right here. Because how is something statistically significant in a multiple regression? Probably one of the easiest questions that we review a lot. To be statistically significant in a multiple regression, you must do what? What must you do to be statistically significant in a multiple regression? How could you be? You've got all these variables, they're all at a party, and you want to be significant. You have to do what? You're fighting against all those variables. You want to be significant, you must do what? Add new information not already explained. Exactly, Nathan. Great answer right there. Technically, pretty well. The only thing, David, good point right there. Small VIF will help. That's generally a good thing. But the only thing is needed is low p-value. But generally, and David, you are correct. Generally, a smaller VIF will help with getting a lower p-value. But statistical significance is only noted by low p-value. But a high VIF would probably increase the p-value. So if you had a high VIF, it's more likely to be less significant. I know, right? It's very, very similar, Wilton. It's like, wait a minute, it's the same thing. And the only real change right here is the deviance. The deviance is the difference from the null model. Like the null model looks like this. More on the null coming up in a second, or the naive, I should say. But the deviance is how much the curve differs. So when you think about this model we looked at a long while ago, why is this curve right here very, very statistically significant? And it's just the easiest way to understand. This curve right here is super significant. And why? Because the curve is not very what? So why is the curve super significant? Because the curve is not very what? So it has a lot of deviance from the naive. It's not very flat. Now the curve is actually a really bad model because it doesn't make good predictions. It predicts no one's donates, but the curve is super significant because it has a lot of deviance from the naive model, which would be the flat model. So right here, even though it's super significant, it kind of looks flat here, but in truth, the curve is pretty, when you zoom out a little bit, I guess you could zoom out on all of them, but it does have some sort of bend to it. So when we do this right here, we won't solve this out, but once again, we're looking at the reduction to the deviance right here in the ways in which it can explain, and the important thing to know right now is going to be the naive model. So what is the naive model? In quantitative data, the naive model would be the what model. When it comes to quantitative data, the naive model would be the what of the data. In quantitative data, the naive model is the what? The average of y. Predict for me, how much do you think a random person at UT weighs? Let's just take a random person, go talk to them today, walk up to them on Ped Walkway and say, how much do you weigh? What would be a good prediction for how much that person weighs? How much do you think that person weighs? 173 might be a good guess. The mean. Max is going with whatever the mean is. Maybe like 150, 160, somewhere in that range. Like the mean, but you got to be like for everybody. The mean for everybody, right? Well, if you were to walk up to somebody and ask them, do you go to UT? And you're at UT, what would you predict? Wouldn't be 50-50. If you're walking around campus and you walk up to someone and say, do you go to UT? You might actually have a naive model like this. I think Nathan's seen it right here. So the naive model might actually be that. It'd be a flat probability because the naive predicts the probability we see for y, the average probability of y. So let's go look at an example of this. If we take the data right here and we look at whether or not people are in Greek life, is not Greek life on here? Oh, we got to go to survey 9. Here's Greek life. Let's do a summary of it. Or let's do a table. If you walk up to a random person, would you predict they are in Greek life or not in Greek life? If you walked up to a random person, would you be like, I bet you they're in Greek life, or would you bet they're not in Greek life? What would you bet on? Walk up to just a random person and be like, hey, are you in Greek life? What would you bet on? And why would you bet that? So you walk up to a random person, you're like, are you in Greek life? What would you place all your money on? I say you have to put all your money on this. You're putting all your money on it. So what would you bet on? And why? Hint why. The why answer's right there. You walk up to someone and say, are you in Greek life? And you got to bet all your money. Not the median. You're going to bet they're not in Greek life. And so think about this. Exactly. And so Nathan, wow, Nathan, top tier answer right there. And Veda, great job too. We would bet they're not in Greek life, and Nathan's already solving out some of the answers right here. We're going to do that mathematically. We're going to divide by the number of rows, and here's the probabilities. We can make this look a little bit nicer right here, times it by 100, and there's that. And we can do an even nicer thing and round it to get some nice looking probabilities right here, and there's the probabilities. So Nathan was finding out the probability because the probability of them being in Greek life is 30.15, and the probability of them not, so it's basically 70%, 30%, right? So what do you think, without any x's, what's the probability of somebody being in Greek life? Just use this information right here. The probability of somebody being in Greek life is what? We could actually draw the naive model. The probability of somebody being in Greek life is 30%. So here's how the naive model would look. There is no x to the naive model. The naive model would look like this, and everybody would get a 30% probability. And the naive model is completely flat, but that's not the mean. That is the probability of the level of interest from just the data itself. And the naive model would predict every single person is what? Because this is the probability it predicts. There is no X for the naive model. No X is down here. That is just the probability of what we're predicting. We're predicting, is someone in Greek life? Yes. So that's the probability for everybody now. So what would the naive model predict for everybody? There's an easy way to remember this in a second, I'll tell you. The naive model would predict everybody is not in Greek life because that is the majority level. Does it make sense that we would predict, well, most people are not in Greek life, so I guess we'd predict everybody's not in Greek life? The naive model predicts the majority level for everybody, and it uses the probabilities of the Y to do this. Like, what is the probability of people being in Greek life with just the Y variable? Well, yes has a 30% probability. No has a 70% probability, so it's more likely they're not in Greek life. So the naive model is the probability of the levels of interest for the overall data. So if 95% of 100 UT kids were right-handed, yes. And the naive model would predict what then? Max, amazing example. You are 100% correct, Max. And then with Max's example, the naive model would predict what? Max, that's exactly right. And great job, Max. Max, that's a 500 point of the day right there, coming up with your own example. What would the naive model predict for individuals? The naive model would predict everybody has a 95% chance of being right-handed, or probability, like over repeated trials of individuals with the same characteristics. And thus, everybody would be what? Since it's 95% probability a person's right-handed, it would just say what about everybody? It would look at everybody and say, well, then I guess everybody's this. It would get people wrong, but it would say, well, 95% of people are right-handed, so every single person. And that's how the naive does. What's the naive going to do? It's going to predict everyone's right-handed, exactly. And so why is it predicting everyone's right-handed with Max's example? Is because right-handed is the majority level. So it just says, well, most people are right-handed. Good guessing that way. You'd be like, you're right-handed. But someone's like, well, yeah, of course, most people are right-handed. You're like, I'm using the naive model. And they're like, you're weird. Naive is the percent change of the indicator being correct. No, the naive model is the starting off point by which we have no X variables and we are using just information in the Y. So the naive model for quantitative is the Y bar, but the naive model for categorical is the majority level. Because if you have a quantitative variable, you could know the mean of Y. Like, let me guess what someone weighs, 155. And you're like, that's about the average weight of people, so that's a pretty good guess. And then the naive model for categorical is the majority level, like right or left-handed. Well, most people are right-handed, so I'm just going to guess people are right-handed. The naive model depends on what? If you're using this data or this data. What did you just hear right there? The naive model would very importantly, because here's a different naive model. Here's a naive model for a different variable, and I have to run different code to get it. There's a naive model 155 for weight. It depends on if we're doing categorical or quantitative. In this example, we might be doing the naive model for quantitative, and it's the mean of the Y variable. In this example, we might be doing the naive model for categorical, so it's going to be the majority level. So it's no information. It's just the Y. The naive means no Y variables. No Y variables. Great job right there, Walker and Nathan. Excellent work. Some more points in the chat. And that's how we do the naive model. That's how the naive model do. So could you... Here we are with a multiple regression model looking at the summary. Same sort of stuff going on. Not too much right there. So pregnant is statistically significant. This means that adding it to the model will reduce the null deviance. Great stuff right there. Basically, it just brings with it new information. And that's what we just got going on. Let's do a little bit on interactions. This is where we're almost done with this. You know what? Should we do something easy or hard to end class? I got my vote. Because there's one, we got two more topics to talk through on this. Easy, I think easy's gonna win. We'll end class with something chill. I like some chill stuff. Remind me if I don't remember to go back and do interactions, and then we need to evaluate the model. Let's go here and do one of my favorite things, checking a regression. Easy's winning out right now. Let's do a checking of a regression. Oh, it might not win. I'll give it a second right here. Give it 6 seconds. 5, 4, vote quick. 3, 2, 1, 0. I could have been outvoted. So when you check your regression, What do you assume about your model? If you have a model, what would you assume about that model? That that's a good model or a bad model by default? If you have a model, now this is, be careful. What do we assume about any of our conditions? If you remember back to checking regression, so this is a repeat topic again, what would you assume about your model if you're checking it? Would you assume, yeah, my model's good, or, oh, my model's got problems? What is the null hypothesis for our model? Is it that our model is good or our model is bad? What do you think? What is the null hypothesis for our model? Like when we think about, is it meeting conditions? Assume it is good. Read, great job right there. We assume it is good. So we are going to assume when it comes to conditions that we are good, and we're going to look for evidence it's bad. So tell me again, do you want a low or high p-value when you run these tests? It talks a little bit about how the tests are run right here. We don't need to know that. We need to look at this. Are you like, yes? Or are you like, oh, no? Who here is happy about this or who here is sad? Your thoughts on these p-values here? Happy or sad? What are your thoughts on these p-values? David and Nathan see it, yep. That's where usually people, great job, Walker and everybody, great work, 100 points in the chat. We're very happy about these. You say, well, wait a minute, but that you're not rejecting the null. But do you remember what the null is? The null was that the curve is a what fit. The idea that we're fitting this logistic curve, and this is what we are literally doing. We're saying, okay, we have a curve that we fit to the data. I assume that my curve is a good fit to the data, and I am doing what to the null? So I'm assuming that this curve that I drew, I'm assuming this is a good fit. And I'm doing what to that hypothesis? So I have assumed that that's a good fit, and then I ran a test, and then I looked at it and I say, okay, I do what to this? Goes back to 201. So I look at that and I say, you know what? I'm going to do what to my hypothesis that that's a good fit to the curve. I ran two tests. I ran my test 1, I say, okay, I'm doing this. And I ran my test 2, and I say, okay, I'm doing this. Use a little stat to 1 lingo. What are we going to do to our null that this is a good fit? We're like, I currently believe that's a good fit. We do not reject it. We fail to reject it. So that means we still believe it. We're like, I don't have evidence against this. At this point, I still think that that's a good idea. We're literally asking, is this logistic curve a good idea? If we had data that looked the following way. Here's the data with the classes. I want you to tell me what the p-values would probably come back for if you fit a logistic curve to this data. Now, interestingly enough, if you fit the logistic curve to this data, the logistic curve is probably going to look something like the naive model. What do you think the logistic curve would come back for p-values for this data? What do you think it would come back for? Because it's trying to fit a logistic curve and seeing if the logistic curve is the proper fit. So what would you, like, that's the way your data looks. That's the curve that it fit. What do you think the p-value would come back for and tell you about that logistic fit? So for that example up there that I drew, if you run the check regression, you're probably going to get p-values close to this. You're probably going to see p-values close to this, giving a ooh, because that does not look good. Hence, you're going to reject the null. Hence, the p-values are probably going to be closer to this. One value in the chat. So the p-values are probably going to be closer to this. 0, yep. Because there's such strong evidence that this is a bad fit. Does that make sense? The 0 indicates to you the amount of evidence you have for is the fit good or bad. We start out assuming it's good till we have evidence it's bad. So if you got a low p-value of like 0, you have strong evidence that this logistic curve is a bad fit. Now, why do we have 2? Well, this is just 2 ways of checking it. We have 1 friend and 2 friends. So let's go look at another example here. What do you notice about our friends right here? We got 2 friends right here. This happens with your friends sometimes. What do you notice about your 2 friends right here? Tell me about it. You got friend number 1, friend number 2. And you say, is this logistic curve a good fit? And friend number 1 says, Friend number 2 says, What do you notice about your friends right here? On asking them, is this a good fit? And this is your friend, is it Laxmi or what is it? Holmser and Lamb Show. And the first one is, I can't remember who wrote the first test, but it's just 2 people who wrote 2 different tests. They're your friends. And you go into them. Method 2 is no bueno. Those friends right here, these 2 gentlemen, I believe, said, nope, you're doing the wrong thing. But this person says, yeah, you're fine, you're fine, you're fine. Totally fine. This is simulated, yeah. So I don't know who made that test, but the first test says, you're good. You're fine. So what's the answer? At this point, it's kind of hard to tell. It's hard to tell if we should be using it. Should we use the logistic curve? I don't know. Maybe. Maybe not. How are your friends doing right here? Tell me about your friends right here. We'll look at our data here at the end of this. Your friends right here on a really complex model with all two-way interactions tell you what? Is the curve you fit a good idea or a bad idea? It kind of says it down there. Is the curve you fit right here, according to the p-values, which have the null hypothesis that we're doing the right thing and the alternative that we're doing the wrong thing? What would it say? This p-value down here, or the p-values for both tests, indicate to us that what? And this is where usually people that are looking at the evidence, we have a bad fit. And here we do not have any evidence. So here we would say we're still good. Our curve is still good. Let's go look at our data from earlier. So exactly. So all we need to do, great job, Daniel, David right there. We're going to run a check regression on our data. And there it is. Ooh, wow, I love it. I love it. Is this still the same model we're looking at? It is. Wow, we got it. Saying this is a perfectly fine idea. Friend 2 saying this is a bad idea. Well, you know what let's do? Let's increase the amount of variables in the model. We are predicting whether or not somebody, where's the model at? We're predicting somebody's gender by their weight, but you know what? Let's just throw all the variables in there. So now we're predicting someone's gender by the weight. Is this a good idea or bad idea? At this point, how do you feel about this? I like the way this looks, and as someone who just ran a bunch of data, I'd look at this and I'd say, what? Do you think I'm okay with this, or do you think I'm not okay with this? What would you say? Do you think I'm okay with this or not okay with this? These results are differing on what they come out with. I've just ran a model with all the coefficients, all the x's in it. So we have a big model with tons of x's. If you look at the code right here, I included every single x to predict gender. And how do you think I feel about these p-values? Who can finish Brian's sentence right here to say, this is how Brian probably feels about these? Because here's the hint. Do you think I'm mad about it? What do you think? This one passes, this one fails. So this one says this is a bad fit. We have evidence of a bad fit. This one says no evidence of a bad fit. So this one would come back and say you're fine on your fit. It does fail the test, and I'm not going to care because this one passed really well. This one barely failed. And sometimes, you know, it barely fails. This one passes fine. So I'm going to say, you know what? I don't think there's that big of a problem. I'm going to look at the model, and this will bridge us into the next class. Because what do you think I want to look at? I probably want to look at how well does my model predict? And when you look at this, how many people were misclassified by this model? This will finish us off today, but how many people were misclassified by this model? So now remember, we're predicting whether or not someone is male or female. How many people were misclassified by this model? So how many people were misclassified by this model? Who knows the answer to that? 100 points in the chat. How many people does this model get wrong? Last two questions. 1 minute warning. How many people does this model get wrong? Great job, Kevin, right there. You see it. It predicted 8 people to be male who were actually female. It predicted 6 people who were male to 6 people who were actually male to be female. So we would take right here 8 plus 6 divided by 699, and that's the amount it gets wrong. And this model, if you did this, think of an A word to end class right here for 200 points. What would you call this? This would be the what of the model. It's how many it gets correct. It's how what it is. 200 points. The percent it gets correct. So it's how what the model is. It's the what. Not quite confidence roll. Good guess right there, Nathan. It's not the confidence roll. It's how what the model is at making predictions. Seconds to go. So it's not quite a confidence roll. It's how what the model is at making predictions on if people are male or female. Not R squared. Just say like, oh, well, we're predicting male, female, and this is how what my model is at making those predictions. My model is this percent, boom, accurate. That's got it. Accuracy. If you hear the word and you like, oh, it's just looking at the accuracy, like how good do we make predictions? And so that's the practice we need. Make sure to remember these words. We're going to be looking at the accuracy of our model and where we make mispredictions. So once again, that is how accurate our model is. And it's the on diagonal. If you take these values right here and divide by 699, you could take this plus this and divide by 699, and that's the accuracy. So, and we could call this the misclassification, or like how not accurate we are. Sometimes it's called the misclassification rate, like what percent do we misclassify, and then the other would be the accuracy. And all that will be covered next time as we go through here and look at the accuracy of our model. And there it is right there, all that good stuff. Predictions, and then we just got to do interaction. So earlier when we had the model with the two category variables, it showed yes, yes, because yes, and there's two yeses. We'll go back to that. It showed two yeses because there are two. There it is right here. Great question, Whitson. Those are both indicators. No is the reference level. Does that make sense, Whitson, right there? No is the reference level. That's why we don't see yes. There's international plan no and voicemail plan no, and those are the reference levels. The reference levels for international plan is someone not having an international plan. The reference level for voicemail plan is not having a voicemail plan. So the indicators for those categorical variables are international plan yes and voicemail plan yes are the indicators. And then we're predicting whether or not someone churns, because churn is the level of interest. Why wouldn't yes be the reference? Because remember, logistic, the level of interest is last. When we do indicators, the reference level is first. So it's a reversal, because in logistic, the level of interest is last, and logistic is talking about the y variable right here, but these are all x's. So when we're dealing with an x variable, the reference level is first. So remember, I am first with references, and in logistic, the level of interest is last. So when we talk about reference levels, they're the first ones, and when we do logistic, the level of interest is what we're predicting, which is last. I know, right? I know. Don't worry. That's such a good question, and just write that down. Be like, reference levels are for categorical x's, and the reference level is first. Logistic has levels of interest, which is what we are predicting. Those are the last alphabetical. Just the easiest. First semester I taught this. I'd reverse it and flip it all the time, but it depends. Are we doing a y variable or an x variable? If you hear the y variable, it's logistic with level of interest. If you hear an x variable, it's reference levels for the thing we're comparing to. Great questions, Whitson. Excellent job. These are the small little things that make it tricky sometimes. And it's just the practice. It's just like repeating it and being like, okay, wait, that's an X, so it's going to have reference levels. The categorical X will have reference levels, and then a categorical Y will have a level of interest, which is what we're predicting in logistic. Level of interest last for logistic. Practice, practice, practice. We got office hours coming up here in 17 minutes. So with that, everybody, Puppet Shark, bye for now. You got it, Puppet Shark. Bye, everybody. Bye.